Okay, so welcome back. Today we're going to talk about the Mortensen Pissarides model, which is a variation, can be thought of as a variation on the Pissarides model. But to do that, I have to explain a little bit what we did last time and review it, and then we'll discuss some of its weaknesses. So the Pissarides model has a few weaknesses, but still it gives you a nice flavor for this flow model of the labor market, changing labor market states, and it's easily extended. We'll use the Pissarides model to construct a more detailed model of the labor market where productivity on the job can actually switch. It can change. So that's the main innovation of Mortensen Pissarides. Mortensen got together with Pissarides and they decided to make the separation rate endogenous in some well-defined sense. And then the neat thing about this Mortensen Pissarides variation on the idea is that you can add all sorts of labor market policy interventions to think about labor market programs that a lot of industrial countries use, like changing the training costs for firms and for workers, changing the level of productivity, segmenting the labor market, adding severance costs. You know, if you have to fire somebody, or if you have to separate. We'll talk about that in detail. That'll be at the end of this lecture. So last time we did the Pissarides model. We did this notion of state changing, finite number of states makes it really powerful. So a lot of my students have gone on to do macro using the Pissarides model. So you can use a variation of the Pissarides model to think about hedge funds, you know, looking for partners in the market, having ideas and looking for someone who wants to invest in you. Or you can think about it, certain types of partner markets. I've used it to think about cryptocurrencies. So it's kind of an interesting idea. So, you know, when you look at this particular module of the course, you'll understand why it's really all about how surplus occurs when you meet someone you're looking for and you see some gain in the trade, and then you have to decide how to split it. So that's the wage determination part, which is very important. It'll be important today as well. And then you need to somehow fix the number of actors on one side or both in this model. And the way that Pissarides did it, which was really brilliant, was to set the number of vacancies in the market by making it really, really easy to enter the market with an idea. So you don't have to really hire anybody immediately. You just have to have an idea to hire somebody. And if there's no limit on the number of vacancies that can be posted, then basically the value of having a vacancy in the market should be very close to zero. And doing that was the key innovation. So yeah, that's probably what Thomas spent time with you guys talking about last time. So here's a review. Here's the valuation. This is like the skeleton of many models with this idea. So if you have some imagination, you can see that it can be applied to lots of different things. Lots of state transitions that are random. Workers face a risk of separation. The match dissolves exogenously at rate S per period, and if unemployed, the workers have a finding probability equal to the product of the labor market tightness term theta times the rate at which employers find workers to fill their vacancies. And these are random encounters, and the finding rate for workers is just theta times Q, right? So F is equal to theta times Q. That's a property of constant returns functions. Very important to remember that. And I do that substitution just to make it easier to play with the model. You have fewer functions that you have to carry around, and that should be easy for you to understand. Okay, so the firm side, similarly, the firms with a work in place, they generate a constant productivity with that worker, and then they have to share it. And the sharing part would be the wage every period paid at the end, right? So then the rest is kind of this logic. At the end of the period, there's a random shock, which is, in this model, completely exogenous. whether it has consequences for the match or the worker and the firm together, is basically a probabilistic exercise. It has very little to do with economics. But that's the first assumption. That's why Pissarides' innovation was so clever. Any questions about that? So, you match up, and then the important assumption is the workers and the firms bargain over the wage. Taking the future valuations as given, the current wage won't affect those future valuations is a very important assumption. It makes it very tractable. So otherwise, then you have to have sort of a strategic sort of path of the wage, maybe, and that sort of stuff doesn't work. It's just not. It's not worth it given the speed at which matches are filled over time. So Pissarides was able to convince us all to use this setup. So in every period, the Nash bargain wage is determined via these Nash products. And the first order condition, given that there's no effect on the future value through the choice of the wage, means that it simplifies quite a bit. So the ratio of those two surpluses have to be equal to the ratio of the bargaining powers. It's a very nice expression. It comes up later on many times in this course. So when you have Nash bargaining, you have something like that. It's also related to the efficiency, the social efficiency of matching. Okay, so keep that in mind too. Those need not be equal. Okay, so there's a potential inefficiency in the Pissarides model that when workers and firms bargain, they have this exogenous bargaining power, but it might not reflect the social efficiency of matching. Okay, and then playing with this the algebra. I'm going to give it to you again just in case, because I tend to ask this on the exam. So it's something you should really be able to do in your sleep, right? Being able to just find this wage equation, because a lot of students look at this and say, well, where the hell did that come from? It's a linear expression. The wage is linearly positively related to B, the fallback, instantaneous fallback of the worker, the benefit, and it's also positively related to what the firm can get out of this potentially, the fallback position of the firm. Think of it that way. It's a weighted average, and the weights are this bargaining parameter and its complement, 1 minus that. So that's very, very powerful, and it doesn't seem obvious how you can get that out of this nasty sort of bargaining, but you can. You just make a couple of strategic substitutions. I'll put that on the slide now so you can take a look at it. But it's really impressive. Okay, and maybe that was just a fluke of algebra, but you can eliminate some expressions that make this sing, basically. The zero profit condition for entering the market with a vacancy and the Nash bargaining setup lead to this very elegant result. It does have some weaknesses. Do you remember the weaknesses? Does anybody remember the weakness of one of the weaknesses of the Pissarides model? Thomas talked about it probably in the section last week. One of the weaknesses is that the wage is renegotiable every period. It's very flexible. And we know from a fact, looking at the empirical data on wages, is they tend to change very slowly. So there's some friction keeping firms and workers from renegotiating the wage every 5 seconds. Okay, so we think that's a weakness because if you look carefully at the Pissarides model, if the wage is as flexible as it is in this Nash bargain, then vacancies and unemployment don't move as much as they do in the data. That was called the Scheimer puzzle. Just give you some preview on that. And that's one reason people have been trying to throw sand into the wage equation to make it a little bit stickier, to make it look more like the data. But it's still, the most powerful message here is that workers' wages depend on the the productivity of their employment with the employer. And if you remember in labor, in the equilibrium condition, the marginal product of labor is kind of related to the marginal rate of substitution. But there's no reason to think that if firms make a lot of profits that it'll show up in the wage. The wage is not supposed to depend on profits, but it does in this model, and that's what makes it such a cool model. Because we know in econometrics, if you do econometric regressions, the wage of workers is positively related to the profitability of the firm that they work for. Okay, so you had a question?
Just like it was about the way this is it's considered a weakness variability every period. But like, what would change in the model that would make the wage changes? So I think even if it was renegotiated, it would be still the same. Like nothing's changed between periods.
Well, you'd want it to be renegotiated in response to new incentives, but not too much. So if productivity goes up, we want the wage kind of to be, I mean, the desire of the modeler would be for the wage to react positively, but not as strongly as it does in this one. Okay, so if you could just put a little friction. So one friction that people use traditionally is to make this wage and last period's wage kind of add up to some actual wage. So maybe the workers just slept too late. They didn't go to they didn't look in the newspaper. They didn't look online what the firm was doing. So they just kind of missed it. So, or maybe a Calvo model where you get blessed by the Calvo fairy, and then you can change your wage. And if otherwise you can't, that's another way of making things sticky. Okay, so these are like tricks that economists use to make the models work better. We know Robert Hall and Milgram have shown that there are better ways. You can have like very sophisticated wage negotiation setups, but you know, we probably need some evidence that this is really what's going on. Yeah.
And also in this Nash bargaining, that all sides have complete information. Am I right?
Correct. Yeah. So you could have. That's a great point. One way to make this work for you would be to have workers learn about their productivity using some Bayesian learning. That would always introduce a sluggishness. That'd be a nice paper. It's probably been done already, but I can't remember off the top of my head. But that would make the current wage a linear function of the new information and the lagged wage, or some lagged expectation. Okay, so that's a great idea. Of course, then you have to say, well, why would the firm know more about the worker? That's probably easy to answer because the manager sees all the workers. In this model, every firm is one worker and one, vacancy. So one firm. So anyway, here's the algebra details. Remember, I told you the key in innovation was Pissarides said, I can pin this model down by setting the vacancy value equal to 0. So if the vacancy value were negative, people wouldn't post vacancies because that's a net loss to them. They wouldn't do that. Why would you do that? And if it's positive, then it's costless to post a vacancy. Let's go. You and I could start a little company selling bratwurst on the Alexanderplatz or something. So the idea is that this knife edge has some economic logic. Because if you post a vacancy, you still have to pay this periodic cost of posting the vacancy, but you have this expectation of getting somebody, and that getting somebody means you can make some serious money, right? And if you don't, you have to keep on paying C. So that's again, it's a very simple model. It's like a bicycle. It just looks beautiful, and it works. It gets you there, and that's why it's still around. 25 years later, it's still actually. He published his first paper probably in 1985. It was in his thesis, I think, too. So it's pretty solid. So if you do that. You set Z equal to 0, then you get two equations for J. Okay, J is the same thing. J is the value in the steady state of a vacancy that's filled for the firm. So you can see it's kind of two different ways of looking at it. One is the firm is getting some periodic profits that it discounts at a higher rate, which is R plus S. That's the second expression. Or you could say, well, if the firm doesn't get a worker and just posts a vacancy for a long time, what's the expected value of the total cost the firm has to pay over time? So that would be related to the finding rate, which is Q, and the expected duration of filling that vacancy would be 1 over Q. Okay, so it's two different ways. So you can put those together and eliminate J, the value of a filled job, and then you can use that. Combine that with the wage expression and the unemployment expression, and you can eliminate all the capital state valuations because we don't really observe them. You don't observe V, you don't observe W, you don't observe big W, big U, or big J. So if that's the case, it's a little bit like value functions in macro. They're nice to think about, but we're never going to observe one. So let's eliminate everything. And if you do that, You can combine it with the first order condition from the Nash bargaining problem, setting big V equal to 0, because it's really J minus V, but V is equal to 0, so that we have this additional condition, and then you can basically eliminate all those valuations. Which you have a little bit of. So that algebra still looks kind of nasty because you've got this Q function in there, but we can substitute that away too, because we know that from the first order condition, we can eliminate C over Q of theta, because it's the same thing as P minus W divided by R plus S. Now, I don't know how Pissarides figured this out. He probably sat in his office for like 3 weeks, and then it just sort of, eureka, bam. But it turns out that's enough to eliminate the Q function. So Q disappears from the wage equation. You can leave it in, but again, Q function is the matching function for matching rate for vacancies. You may not have your hands on it, but it has to be equal. It has to be related to the surplus valuation from the firm's perspective in the way that I just mentioned. Okay, so this last expression here. So then you get the wage equation. And then you just solve for W. Okay, so it's really, really interesting and useful and important. You can take that W value, little w, the wage, plug it back into the valuation of the firm, and then solve for the relationship of vacancies to unemployment in equilibrium. And you see that it doesn't show up anywhere in that last expression except as theta. So it's always the ratio V divided by U. Remember, theta is this sort of magic measure of labor market tightness. V goes up, more vacancies per worker that are looking for a job, unemployed workers. And when it goes down, the labor market is slack. Okay, so that thing looks like a ray from the origin. It's positively sloped. I'll show that in a second. You can call that a vacancy supply curve, but it's really it's an expression for theta. So when theta is high, vacancies relative to unemployment are high. But if theta is constant, then it's really just a rate. It's a scaling up of the labor market. The same value of theta can correspond to a large number of vacancies, a large number of unemployed people, or to a small number of vacancies, small number of unemployed people. Okay, that's the first upward sloping. The other one we already derived, which is the stock flow condition for unemployment. Remember, we just took when unemployment stops changing, it has to be the case that unemployment is the ratio of the separation rate to the sum of the separation rate and the finding rate for the worker. And if you just look at that, that's equal to the scaled value of the matching function, just a function of V over U. Okay, so we have two equations in vacancies as a rate and unemployment as a rate. And those curves intersect. It's like supply and demand, right? It's beautiful. Everything we do with Mortensen Pissarides will look like this as well, but just different axes, This is really easy. Any questions? Okay, it gets more fancy when you start moving things around because then curves start to shift. That's the whole point. And I like shifting curves. If you get them right, sometimes you have to be careful not to make mistakes. But that's what the math is there for. That's why those formulas are there, right? So anytime you see theta, we're thinking theta is equal to V divided by U, right? So that's really nice. You can use math to show that rigorously, as far as we can do in economics, with the assumption on the matching function kind of translates into the shape of these curves, and we've already assumed constant returns to scale. So Luxembourg, Berlin, the United States, they all have the scalability property, right? That's an assumption, but it works pretty well with data. And you can also show that the VS curve is positively sloped. Formally, I told you already, but remember this. It's useful for your life. Anytime you have an equilibrium condition, someone's going to ask you in a seminar, well, why do you think that this is going to be the case, that if you increase this parameter, you get this result? And normally you do that using what we call comparative statics analysis. I do this in my other labor course. If you took that, it's always coming back. It's basic stuff. In dynamic models, you have to be careful because things are changing. Maybe you just want to look at the steady state first, and that's what we're doing here. This is a steady state comparative statics analysis. Okay, so here's an example for the UV curve. I kind of alluded to that last time. It always helps to kind of massage the condition to make it less complicated. So when you take the derivative, you have fewer incidences of the chain rule or the product rule, just to make it easy for yourself, but you always get the same answer, right? And I told you there are two different ways to do this. You can assume that V is an implicit function of U. Okay, so we differentiate the entire thing with respect to U and see what happens. That's what I do in this example. Okay, this is what I learned when I was in college. And then you just solve for the derivative dV du, which is the slope of the UV curve. Okay, that's pretty easy. And you can see that it's unambiguous in this case because we know S is positive, right? We know that's a negative of a positive, must be negative. And we know that the derivative, the matching function with respect to U is also positive. So the numerator has to be what? Has to be negative, right? Minus times positive, negative. In the denominator, we have unambiguously positive thing. So ratio of a negative to a positive has to be negative. Okay, so that's kind of brainless comparative statics analysis. But it's important because every assumption you make about M shows up here. And remember, M is the matching function. So if you hold vacancies constant, you add more unemployed people to the mix, you get more matches. That's the assumption. And it's actually very well documented in the data. It's just that there aren't enough matches to make every unemployed completely unemployable employed because we have a diminishing returns at the margin. Right? Yeah.
So there's still a U and a V in the derivative? That's why it's not a linear curve?
It's a function, yeah. M is a function of U and V, and the first derivative is a function of U and V. So those are suppressed for simplicity, but if you wanted to, you could write it out. And you could write out these things as being, this is a function of U and V, and this is a function of U and V. And these derivatives are evaluated at a point, right? I mean, this is not an absolutely general constant value because we can have different values of U and V at different equilibria. So yeah, it's a very good question, very good answer, I think. Just don't forget that, okay? You can also, do the same thing for the VS curve. And here it's if the VS curve tells us that holding all the parameters constant, theta is constant, then it must be that U and V are changing at the same rate, and they are, right? That's what dV du is equal to the ratio of V to U says, because if you divide both sides by V and divide both sides by U, you get sort of like the rate of change of V and the rate of change of U are equal. And that's like saying the ratio is constant. Okay, that's just a little subtlety there, but that is a fact. But as soon as I start changing the exogenous parameters, then the VS curve might change its slope. Yeah.
Just a question about the matching function. We don't need to assume in any case in this race model that everybody is matched, or
They won't be. Think of the matching function it's like a meat grinder. You got to put some meat and some spices in there, and at some rate you will churn out these people that come together, but not everyone's going to make it in a unit time. So, and you have people losing their jobs at the same time, so you've got this, it's the bathtub, right?
Yeah.
Meat grinder in a bathtub.
just like
I love how to think in terms of pictures, right?
just like for sure, professors, that these models are being used in monetary economics. So
Sure, of course.
They use it just like for a simplification assumption always that the short side of the market is always matched, or like in equilibrium everybody's matched.
No,
Yeah.
no, because you have, it's a stock flow equilibrium, so the matching function captures the flow. It's a function of two levels or two volumes in the bathtub, volume of vacancies, volume of unemployed, and they just can't be matched. That's the whole assumption. It's just there's not enough information, there's not enough congruence of vacancies with unemployed, and then it just follows out of the logic that, and we'll talk about comparative statics of increasing the efficiency of the matching function. You can do that. And if you make it really efficient, then the level of unemployment will be very low. There won't be any unmatched anything. But you still have to have a theory of why people would post vacancies under those conditions. So this is a completely consistent model. And if you move too far in the other direction, you might risk making really absurd situations. And when you say the short side of the market, that's the old-fashioned way of thinking about labor demand and supply. The advantage of this is that there is no short side. There are people on both sides. They're just not getting matched. Yep. Now we don't always know the matching function. We like to use Cobb-Douglas because it's Cobb-Douglas, right? It has constant elasticities. So the elasticity of matches with respect to both of the arguments is constant over the entire range. That's the power function. And it works pretty well with a lot of people. I even wrote some papers on this. You actually try to estimate it using cross-sectional data or time series data. It does actually fit. One has the feeling that there's some other things going on that we're not, but you can't reject constant returns either. So it's not a bad approximation for small changes. But we know the constant elasticity of substitution will be a generalized form, or you can use a translog form. There are lots of different forms that you can push into this M function, and if you know the M function, then you can actually solve for theta in the equilibrium. Okay, so here's another example of what you can play with. You can actually look at the other terms that sometimes they affect both curves, so it gets a little nasty. That's why you have to use comparative statics, because these will cause one or both curves to shift. So one of my favorites is this efficiency. So take M and just multiply it by something. So it's like Hicks neutral technical change. So if A goes up, then the meat grinder works better, okay? And you can think of all sorts of, correlates in the real world. I mean, if you go to the Lausitz now, there's a lot of people who work in coal, and coal is not a great sector to be in these days. So those people who lose their jobs in the Lausitz probably don't have the skills set they need to work in a steel factory or a Tesla. They might have some overlap, but there might be some friction involved. Or if you're in a world where information doesn't flow very quickly, so Germany before Hartz III, the Hartz III reforms increased the efficiency of the employment agencies in Germany, or the establishment of a data bank or private job brokerages, that sort of thing. So a lot of people actually use this to think about finance. How do I find an investor? How do I find someone who wants to invest in me? And you can use this. So this time I'll use the total differential, which is, again, it's calculus, different cut. It's like the Leibniz approach, I think people call it sometimes, as opposed to the Newton approach. I don't know. I can't remember exactly which one it was, but you take, this is what a lot of Germans do when they're in the Leistungskurs in Mathematik. So you can do this. It's just a linearization, and you're taking the small changes. So if this is, to me, it's very intuitive to think about this. When you take the total derivative, you're asking what can change holding the equilibrium condition constant. Okay, and some of those things that can change are exogenous, like A or S, and some things are endogenous, like U and V. And then I just have to decide what I want to hold constant, ceteris paribus. So I set dA equals 0 and let ds be positive, and then solve for their effects on u and v. But then maybe I just want to look at one, so I'll set dv equals 0 and look at du. So what do I get? I get du ds, right? So you have to take this huge derivative, total differential we call it officially, and then solve for the derivatives of interest. Okay, so again, it's just a mechanical way of doing it. You can do the same thing we did before with what's called implicit differentiation, but here we can solve for dv ds or du ds or whatever. And you can show unambiguously that the UV curve shifts upward in the case of an increase in S, which is the rate of job separation. So it'd be like comparing a region where tourism is very important with a region where healthcare is very important. So the flow in healthcare is very low. The inflow into unemployment, the inflow into unemployment in tourism regions is very high because you have seasons, right? People lose their jobs in the off season. And that would cause the curve to shift up. So you can do the same thing for, excuse me, I didn't synchronize this very well. You can do the same thing for vacancies as in response to arbitrary change in A, the efficiency of matching along the UV curve. And that would be, remember, A is like the efficiency, so the more efficient the labor market is matching, the lower to the left the UV curve will be. So it's kind of like a way of showing that. Okay, because M is positive. Remember, M sub V is the first derivative, partial derivative of M with respect to V, and that's positive. So minus times something positive is negative. So the shift is negative. So this is just a general technique that we don't teach enough. This is interface between mathematics and economics. A lot of people can tell a good story, but if people start to push back, you have to show it, right? You say, okay, I've assumed this, and this is what I get. And then you convince them. So mathematics is a kind of a vehicle for convincing people. Okay, so this is something you should think about. This is why we do this, ask all these questions, and the Pissarides model is very simple. So you're going to be doing something like shifting the VS curve in a clockwise or a counterclockwise direction, and if you're playing with S and A, you're going to be shifting the UV curve, and sometimes the shift in S and A actually affect the VS curve. So because they affect the matching function, and they affect Q. So you have to really be careful. I'll give you the easy ones are the ones that have easy answers, and sometimes the answers are ambiguous. So in this case, you can see it graphically. An increase in separation shifts the UV curve outward, so it makes matching harder for any level of vacancies and unemployment, but it also changes the incentive of firms to post vacancies. Okay. One way of thinking about that, the way I like to think about it, is that a vacancy, if placed, doesn't last very long because it gets blown up. So if you post a vacancy in the tourist sector, or nowadays in Berlin where the labor market is really hot, it's really hard to find workers now to do anything. Because as soon as you hire them, they say, I found something else. Or I don't want to work here anymore. I don't like the color of your hair. And then they just leave. So that's the higher the turnover, the less profitable the vacancy is. So that would cause firms to post less vacancies, ceteris paribus. That would cause the VS curve to flatten, and you can show that formally. And therefore you get this interesting ambiguity. Okay, you get an increase in unemployment, but you don't really know if vacancies increase or decrease. You can see it just by looking at the picture. But unequivocally, we get more unemployment. This is a lousy development for workers in this model, if the separation rate goes up. So, without talking about welfare, just talking about the value of the unemployment rate, the number of workers in the labor force that are just swimming in the bathtub looking for work is going to go up. Okay, and the matching efficiency, we call that A, the sort of the shift, the level shifter of the matching function. If that goes up, that means that it's easy to find workers. So it's also easy to find workers if you're posting a vacancy. So that kind of increases the capitalized value of having a worker in place. So that's going to make firms post more vacancies, so you're going to have more entry, so that's good for workers. Okay, and, well, for workers, it's easier to find a job, so that's kind of interesting, and no matter, for a constant level of separations, their lifetime income will go up. So this is kind of a good development for everybody, as far as I can see. Could probably tell a story where vacancies actually go up in this case. Okay, you should look at it carefully. It all depends on the extent of the shift. And that's why we need to use calculus to get for an exact expression, and we can actually say it's ambiguous, right? Depends on this, and if I know this, then I can show that it's always positive. Not always. Okay, so this is good for workers. If you think unemployment rate is a measure of in this model, the number of workers in the bathtub looking for work is going to go down unambiguously. Yep.
Can we say that a lower vacancy rate is always better for the firms, or a higher one always worse, or is that not as clear?
No, you need to look at the value. I mean, again, this model is really not great at saying whether you're better off or worse off. You have to have some statistic, and one would be the J, right? So what is the unconditional value of the match given that you've got a worker in place? And that's equal to P minus W divided by R plus S. Okay, so that's one way of expressing it. The other is C divided by Q. And Q has A in it. So depending, A is the firms like the ability to find workers, and that would be increased by this. But it also makes it less valuable in terms of the alternative, which is these vacancy costs. So it's tricky. It's going to depend on which one moves more. So that's why it's ambiguous.
Could you explain the intuition behind why the UV curve shifts but the VS curve flattens? I know you mentioned it, kind of.
This one? It's a different. These are two different exercises. Here you get this one.
No, not between the two different graphs.
But okay,
Kind of the two different curves. So how the UV curve changes,
Okay.
shift it, and the VS curve, the slope changes.
Yeah. Well, the VS curve is a different economic phenomenon. So it depends on basically firms being indifferent between firms that don't have a worker posting a vacancy or not. And there's an infinite supply of these guys. Okay, so they just, as soon as it's vaguely profitable to post a vacancy, they'll do it. And that keeps it at zero. That's going to depend on the prospect of placing your idea with an unemployed worker. And that's going to depend on the ratio of V over U. And that's different from the success probability, given the vacancy in the pool, of finding a worker, or a worker finding a vacancy. And that latter relationship is the UV curve. Because that always shifts in when A goes up. Because it just means that if I had a 50% chance of finding a worker before with the same vacancy, now I have a 75% chance per period of finding a worker. So you can flip it also from the worker's perspective. It's kind of a win-win for everybody. But for the firms trying to find somebody, it's not so obvious, because you have this endogenous reaction of other vacancies which crowd you out. So that's the whole magic of this model. You have these externalities everywhere. You have workers love when firms post vacancies. It makes them more powerful. It makes their wages look better. It doesn't make them more powerful. It makes their fallback position more attractive. And firms actually don't like other firms posting vacancies because it makes their chances worse. Right? Okay, so we can do all that. You can even look at the interest rate. The interest rate has an effect here. We didn't talk about it, but it's true. The more you discount, the less you place value on future flows of your investment in vacancies or in having a worker. The more you're going to value the present. So that kind of tends to raise unemployment, actually, in this model. But you can do this on your own. These are the easy ones, and like I said, UV shifting sometimes changes the VS curve too, so you have these ambiguous outcomes. Okay, so what are the critiques of this model? So as soon as you put a model down in a seminar, present it in a seminar, people start throwing rocks at you, eggs, you know, and you have to defend yourself. So Pissarides was able to defend his model and wrote a book about it, 2000, MIT Press, great book. You know, we have a real story for why firms post vacancies, because before it was like labor demand and supply, and you tell a little side story about what a vacancy is. What is a vacancy in the Marshallian picture? What does it mean? It doesn't mean anything, because by definition, firms can go to the labor market and just hire whoever they want at the going wage. That's Marshall. Nice model, not always perfect, but we like it. You can use it in all sorts of contexts, but if you want to explain vacancies, good luck. Okay? It also explains what it means to have frictional unemployment. It also highlights Lucas's idea about the value of a vacancy, or value of having a worker in hand, or the value of a worker who just lost her job, right? Or a value, and again, what does it mean? A value of worker, I'm talking as if these people have value, but it's the value of their state. How much income can they promise themselves, can they expect from having a job, given that there's all this turbulence going on? They can lose their job every period with probability S, right? So that's kind of the brilliance of the, okay? And it also gives us a hint on this Holsheimer puzzle, which Thomas will talk about, this notion that the model is so cool, but it doesn't explain on the face of it why the quantities are moving so much and the prices are kind of sticky. Okay, if we're given fluctuations in the productivity of the match, the Pissarides model would suggest that the wages track productivity pretty well, and therefore the theta wouldn't move so much. But the fact is, theta moves like crazy. I'll show you in a second. It's like, it's incredible. And that was what Hall and Scheimer discussed in 2005, discovered it. I mean, people kind of knew this, but they just didn't understand the model really puts a restriction on how much volatility you can explain. So you need to have a story that says the prices are kind of crunched, and that makes the quantities jump a lot. And that comes out of this model, but it doesn't come out automatically. You need to have a story, okay? And again, if you look at the wage equation, there are lots of cheap ways of getting this to work. Okay, one of the cheap ways is to say that B, what is B in our model? The benefit, because benefit, but it could also be your mother-in-law giving you money, or your, Burda again, all these things. So the trick, one of the tricks to make this work is to push B very close to P. So the range in which B and the wage moves is limited by B and P. So if you make it really tight, there's a paper that said, let's try 70%. So the workers fall back. So, again, it's not just the benefit. It's also just, maybe you want to take a break, go on vacation, hang out, watch the Champions League. And some people really do that seriously, right? I mean, you're all academics, and maybe some people actually get a lot of utility, and you have to really push them to make them go take that job. Maybe they earned a ton of money and they don't care, right? They're just living off their savings for a while, or maybe they won the lottery. So some people may have that, and that would push B close to P. And if you make it almost, you make that band of fluctuation, you make the wage move in that band of fluctuation. So you mechanically make the wage rigid. So that's the cheap way of doing it. And more sophisticated ways would say, well, it depends on the past. Workers are irrational. They don't read the newspaper. They have a Calvo ferry. It makes them able to. So all these things can be done. But you need the wage rigidity. What about the weaknesses? What are the weaknesses of the Pissarides model? If you want to be critical in a seminar, you got to get your eggs ready and start tossing them. As soon as anybody, just economics is not about being nasty, but sometimes it's close.
Exogenous separations,
Right. Exogenous separations is the big weakness. And the exogenous separation suggests that the matches are not as homogeneous as they are in this model, in reality. Because we know that you have highly valued employees, you have pretty highly valued employees, and you have really lousy employees. Talk to any manager, and they'll, if you can give them like the truth serum, they'll tell you that. And then if I could get rid of this guy, it'd be great, you know. And, you're not supposed to talk about that, but that's the way it is. And workers are different. They are different. And sometimes workers are different because they just don't match after the fact. You know, it's like the key that doesn't work. You can get it in there, but you can't turn it. It's the same thing with match productivity. And maybe it's not the worker's fault. Maybe it's the firm's fault. Maybe the firm is a lousy manager. Maybe they're just nasty. You know, maybe it's a very unpleasant environment. Maybe the temperature is too low because of the crisis. The manager turns it down to 16 degrees instead of 18. So there are all sorts of ways to think about this. And in this model, you don't have any rejections. So, you know, the only reason you split up from a firm is that S, the event with probability S occurs, and you just break up, and everyone's mutually okay with that because that's it. Well, in fact, maybe that's not the way it is. So that was a big weakness. And that's the whole idea of this course. As we move on, we'll start talking about reasons that people walk away from matches. You know, you have an interview, and you say, wow, nice place, nice location, lousy boss, or I don't like to work in this part of town, all those things. So you can squeeze that in as a good excuse to hammer the Pissarides model. Yeah.
Are there versions of this model or similar ones with incomplete information?
Sure, of course.
That
Yeah.
seems, at least to me, like a big one.
Mm-hmm. Yeah, we'll talk a lot about that in this course.
I don't know what else is out there.
Yeah.
I don't know.
So go to the Moodle page and go forward like 6 or 7 lectures, and we talk about that. And then this, someone said it already, exogeneity of the separation rate. And that's just remember the unemployment rate, in fact, is the ratio of the separation rate to the sum of the separation and the finding rate. It's just a beautiful fact in this whole bathtub world. And right now we've only been playing with F, the finding rate, by changing theta, the ratio of vacancies to unemployment. But in fact, maybe S is changing. Maybe it's changing over the business cycle. It does change. It doesn't have to change very much to make the unemployment rate move a lot because it's S, small number, divided by S, small number, plus F, large number. So 1% change in S actually has a big effect. A 1 percentage point change in S has a huge effect on the unemployment rate. Okay.
Is S that much smaller than F?
Yep. Fun fact. And you can see it, okay? So take a little break from the slides. You know, if U is equal to S plus F. The number in Germany, what's the unemployment rate in Germany?
4%?
Let's do 5. Just for fun, okay? Now, I'll tell you that the exit rate is 25% per month in Germany. That's probably an underestimate. It's a hot labor market right now. So what do I need to have a steady state here? Just do the math in your head quickly. To get that number, I'm going to need a really small s. Okay? And it's a rate, so a percentage point change in that rate is just huge. Okay? In fact, we talk about percentage change in that rate. Okay? So let's just try one for fun. Let's try 1% per period, per month. Is that going to work? I think it's a little bit too high. Maybe not. Anyway, something like that is where we're looking about. And you know, if you go from the labor market for people in office, sort of Sachbearbeiter, okay, it's really low. And if you work in the construction industry, you have a S that's pretty high. So, I mean, high meaning that when the job is over, you may actually become unemployed, even though you shouldn't, because it's a job right. But it makes sense to become unemployed for a while, because then you can just collect your mind, maybe go to Ibiza, check it out. Yeah.
But so that comes because the denominator for S is.
It's influenced by both, right? And then this one is much larger, just a fact. This one's larger.
But like the job finding rate is like job finds divided by unemployed people, right?
Yeah.
And then for S, the denominator is like the workforce. So
No.
also
It's employment. Employment. Yeah.
But that's still a
That-
way larger number than the unemployed.
Thank goodness.
Yeah. Okay.
But it could be, we could imagine a world where S is extremely high, people lose their jobs every day. Actually, some migrant workers in the United States, they have to start over every day. They literally go to a hiring hall, and they say, I want to work today, and you have to go here. It's brutal, but if you do the CPS question on those guys, they're actually losing their job every day, right? But they also find a job very quickly. So it's a race. That's the way it works. Any other questions? Okay, so now let's expand our horizons. So we've learned about the Pissarides model. Let's try to up the ante a little bit. Let's make it a bit more all-encompassing. So Mortensen met Pissarides in the early 90s, and they started thinking about this, and especially probably Dale Mortensen said to Chris Pissarides, I think this is a great model, but S should not be exogenous. Even small changes in S can make big changes in the unemployment rate in the data. We need a model that connects this to this and gives us an unemployment rate. So the similarities are clear. It's basically a souped up Pissarides model. That's why, I'm sure Dale would agree. He's no longer with us, but he was a cool guy. He actually visited the Humboldt University in 1997, I think, or 98. I invited him, and we had fun. It's general equilibrium in the sense that these models are general equilibrium. So it doesn't look at consumption or investment, but it looks at certainly at simultaneous determination of vacancies and unemployment. You have the search and matching frictions. So that's a key aspect. And again, just think of this as, you're in the dark, you're trying to find somebody, and you eventually bump into them, and then you can have an interview, and then if it works, then it works. But the key thing in this model is that there's heterogeneity of the match. That's the key thing. So when you're in a match, the productivity between you and me, I'm the employer, you're the worker, is not constant. It's changing. It's evolving over time. And there are many ways to do this. And Mortensen Pissarides were the first to do this in a way that's so tractable that any master's student can understand it. There are harder ones that involve harder nuts to crack that we can crack at the end of this course, but not now. So I'll stick with MP 1994. This original paper is really poorly written. I mean, I can say this because I'm, an old timer, but the book is fantastic. So Pissarides in the 2000 book does a great job making it understandable. Because I think when they published that paper in the Review of Economic Statistics, it wasn't really clear to them what they were doing. And it was such a revolutionary idea, it got them the Nobel Prize with Peter Diamond. So we have heterogeneity of productivity on the job. Okay? So, and we're going to call that X. So X is it goes between 0 and 1. And that's all I'm going to tell you right now, but I'll tell you more in a second. Here's the second. So the innovation and the simplicity here is that basically when you meet a worker, it's in the bathtub, you start out with X equals 1. So you have full productivity. But what happens is the longer you're with this match, the higher the probability that something will happen. And when you start at the top, it's it's always going to get worse. So your boss doesn't smell very good, or he's nasty, has bad breath, or maybe he's trying to molest you. I mean, all these things can happen, and that would make the productivity go down from 1, because it starts at 1. Okay? Again, this is just to assess the idea that over time, things can happen. Things can get better. Can get better. So you can have a bad shock, and then you can say, well, this guy isn't so bad after all. I think I'll stay here, and then you can move up. The point is, it can move within a range of acceptable levels of productivity, and after that, you say, we call it quits. Okay, we break up. So that's the innovation. And we're going to use this notion of a Poisson arrival of the event, of a change in productivity. And that Poisson intensity parameter, we're going to call it lambda. Some people call it a Poisson probability. It's not quite accurate, but it means in a small interval of time dt, the probability of this event happening is lambda times dt. T is time. Okay? So this is a magic assumption that search theory uses a lot. Okay? It is very robust. And one of the first persons to think of the Poisson process, or the Poisson arrival probability model, was Poisson, who was French. And one of his competitors who didn't get much credit for it, is Burda, who was a professor of statistics in this university. Okay, turn of the last century, late 19th century. Professor Hertler calls himself the Burda professor of statistics. So Burda actually also thought of this independently of Poisson. He didn't quite do it as well. He wasn't very good at marketing. And he was actually doing a study of the probability of getting kicked by a horse in the Prussian army. Okay, so this is, very useful information if you're a military commander. And the whole point is, the longer you wait, the more likely it is that something's going to happen. That's all you need. For small changes, it's linear in this parameter, in time. Okay? So just keep that in mind. So you start at x = 1, and it's like dating. You're going out with somebody, and then you start learning about all these not so great attributes, and maybe things get worse. They can get better, and then get worse, and that's the same thing with a job. You start working with a job, you have state-of-the-art productivity, and over time things kind of deteriorate, maybe because the world is getting better behind you. But in some sense, you're trying to model this heterogeneity in a way that's tractable. That's what economists do. We have to find a tractable model, and then we go for it. So you had a question? You had a question.
Is all of this in the period before finding the job? So X, is it affecting?
No, it's when the job commences, it's X = 1. Otherwise, you're just in the bathtub, and you're completely unmarked.
So X affects the separation rate, not the finding.
Right, exactly. So we don't have, this model is not that advanced. This is a model about heterogeneity on the job, as opposed to heterogeneity of workers looking for a job. Again, it's just, trying to make slices at a very difficult problem. And later on, we'll do that. You'll have different workers with different skills, and skills that are unobservable, and you have to learn about them. I mean, it's really hard. So we start with this wonderful model. Question?
This assumption that productivity is high at the start of the match and then maybe tends to deteriorate, is that something that we can see in the data? It seems to me that maybe separations are higher in the first year or so of getting a new job. So for example, you don't make it through prototype or something.
Yeah, that's right. Okay, so.
There's like lots of people who work 30, 40 years in their companies.
Okay, so there's a set of papers by Ramey and some other people that have looked at the consequences of starting with some other productivity than the top. It doesn't change much. It doesn't change the qualitative predictions. It does make the model much more difficult to play with. So, I've been teaching this for a long time now, and I've just decided not to go there. But if you want, it's a nice paper to write a thesis on. I mean, you can evaluate, but the differences are second order. They're first order for things you talked about, the probability of losing your job at the beginning versus the middle of a career, And, but there are other countervailing forces as well, which are quits, right? We haven't talked about this model has no quits. And if you have quits, then you can kind of add another variable to this model. So people tend not to quit if they see a high trajectory of productivity for themselves, and that translates into a wage. But if they see that the boss doesn't want to pay the wage, then you have to have a model for how the wage is determined, and usually it's Nash bargaining. It could also be you agree to a contract at the beginning, so you negotiate over a profile of wages depending on your productivity, whether it's measurable or not. So there are all sorts of variations. We'll stick to this, okay? Again, why? Because we want to get this to respond to things. We want to let S vary in a way that actually makes sense. Again, I said this already, not just because of the tourist industry versus metalworking versus office work, but rather also that maybe the spread of productivity could matter. Okay, here it won't matter immediately, but I can scale it, and other things. So let's give it a shot and see what we say. So again, the Poisson kick is really literally just the probability associated with in dt of having something happen, but then what happens? And that's where it gets interesting. When something happens, I put my hand into the hat. The matched worker and firm, put my hand into this hat or the urn, and I pull out a value. Okay, and it's going to be coming from a known distribution, cumulative distribution of f. Okay, and all I need to do is want f to be continuous. So it could be the normal, but it can't really be normal because it's bounded. So we have to be a little bit. It could be a truncated normal. We'll probably generally use the uniform distribution. That's easy, right? Just to make the point, because then you can solve for the probability, the cumulative probability of not being shocked. It'd be 1 minus x or something like that. But you can use more general distributions, but they may not be analytically tractable. So you'll have to use the computer again to solve it. So now this is the most important part you should remember. And this is why I teach this, is because this is your first encounter with the reservation property. The reservation property is a characteristic of optimal stopping. At some point, you say, okay, this is it, right? This productivity is so low, I don't want to be with you anymore, period. It's not worth it. And then you separate. It's like getting divorced. Okay, in this model, it's all very clean. The divorce is clean. Can't go back and say, I made a mistake, slept in my own apartment for a few months and I kind of miss you. That doesn't happen here. It's over, period, boom. So the job is destroyed. And the optimal stopping property means that there's a critical value, and Mortensen Pissarides calls it R, reservation level of productivity, below which we destroy the job. And we both agree. So this is a model of mutually agreed job destruction. This is not what we observe all the time in the world. A lot of times the management says, I really don't think you're very productive. And the worker says, yeah, I'm productive. Of course I'm productive. And then you have a disagreement. No disagreement here. It's all transparent. You have to start somewhere. Con algo hay que empezar. Right? You have to start somewhere to get anywhere in this world. I was hoping that the Cuban guy would be here so he'd be impressed with my Spanish. Anyway, you got to start somewhere. We're going to start with this one. And this reservation property will translate into a whole bunch of models that are important to us, which is the reservation property. When you're searching in the bathtub, you run into somebody who makes an offer to you, a certain wage, a certain job condition, and you say, I'm going to keep looking. Or, yeah, I'll keep it. Or here's a reservation property applied to an existing job where the conditions are changing, and then you can split up or not. Right? And again, mutually agreed in this model. So again, it's kind of restrictive, but I mean, I've worked on models where you set the wage, and then you always have disagreement because the wage can't adjust, the world changes, workers say, I love this wage, even though I know I'm less productive, and the firm says, I can't pay this wage, or I don't want to pay this wage. So then you have disagreement. And that's what happens when you get away from the Nash bargain. Okay? I'm telling you too much right now, but you should understand that all these things come together. The history of economic thought in this modern age starts with Pissarides. You could say it even starts with Diamond, then it goes to Pissarides, and then it goes to Mortensen Pissarides. But there's much more coming up in the future. Yeah.
Does the wage adjust to the new productivity
Yeah.
value?
Of course, yeah. That's why you have this mutually agreed thing. So, the worse the productivity goes, at some point it gets very close to this reservation. So both parties will agree, let's call it quits. Let's divorce. And then they both go into the bathtub and do their thing.
And is big R somehow related to this fallback position?
Oh yeah. I'm about to derive it. I'm just describing it right now. I haven't even gotten anywhere close to characterizing it. So that's the background. Now, immediately we see that the separation rate, and I haven't told you anything yet, but we know that S is now got a form. S is the probability in the next instant. It's a continuous time model. It's not the same as the Pissarides model, which was discrete time. We can actually do this in continuous time. Every instant, we have a probability of getting a shock, and multiply that by the probability of getting a bad shock, which is F of R. It's the cumulative evaluated at capital R, is the probability that we divorce. Okay? And that's equal to S. So we already have a theory for S, even though I haven't derived it yet. Right? You got a reservation level of productivity and this lambda, this Poisson intensity parameter of getting hit with some shock. Things can get better. We've been married. We're getting close to the edge, and then suddenly I realize, wow, this is not so bad after all. So that would be a positive shock, right? Put your hand in the urn, you pull out a nice value of X, and suddenly we're far away from them. Now I want to derive those. I want to characterize and derive those endogenous variables, because the endogenous variables are now R, the reservation value, and theta, which is the labor market tightness in the Mortensen Pissarides model. And by extension, that means I've also characterized V and U. But the famous diagram for us will be R and theta instead of U and V. So it's getting more fancy. So we have the following concepts. We have matching, just like before. So if you understood Pissarides, you'll understand MP. There's no decision of whether I search more intensely or less intensely. It's all kind of exogenous. It's like you're in the bathtub, you're swimming around, and you're bumping into potential partners. The model is cooked that every encounter will be accepted. So that's the difference between Ramey and all these other people. I forgot the other guy who does this stuff. And this model is that you always start at 1, so it makes it easy. There are no rejections. If you have heterogeneous productivity at the inception of the match, then you could have rejections at the get-go, and then you'd have to write that down, and it's more complicated. This is simpler. You want life to be simple, not too simple. So we've got this matching function, looks like a production function, has all the same attributes, so if you understood Pissarides, you understand MP. And it's linear homogeneous, so we have constant returns to scale, and we can scale it up by some arbitrary size. Okay, and we got the same contact probabilities as before, all the things I talked about earlier. If I tell you Q, you can tell me F. So I only need to specify Q if you know constant returns are true. Right? And if you don't believe that, take a constant returns function and try it out yourself. So the easy one is Cobb-Douglas. We put that on the exam time sometimes. So I give you a Cobb-Douglas matching function, and you can show that Q times theta, Q of theta times theta is equal to F, and vice versa. So you only need, right? But you can also do it for a SES function, constant elasticity substitution, matching function, or some other bizarre matching function, the earn matching function. They're all a bunch of interesting derivations. So we still have this interesting aspect that the tighter the labor market is, from the perspective of the worker, the less attractive it is for the firm. So the firms are like unemployment, and this is what Karl Marx observed. We already mentioned that. Karl Marx talked about the army of the unemployed, because he saw that as a way of keeping wages down, right? So it's always good to have a little recession here, make workers a bit more docile. That's in this model. You don't have to be a Marxist to accept that. It's a fact, and therefore capitalists complain when labor markets are tight. So in Germany, until the pandemic, the firms were complaining, we need to train more workers, we need to import people from Syria, from Ukraine, because we can't find any workers. Well, why? Because it's very expensive for them to find replacements. Okay, so it was great for the workers. Workers, where they could, were getting better wages. Germans don't like to negotiate over wages. It's my impression. But you can always quit. You can quit and let your ex-employer cry. So again, think of these, in a continuous time world, think of these unemployment spells, we call them spells, is kind of how long have you been unemployed? Have you been unemployed for 2 periods? Have you been unemployed for 5 periods, 10 periods? Okay, those are actually, in this model, with constant placement rates, finding rates, are like random variables. Okay, so a large number of people may find a job in the first period, but even more people will have found a job in 2 or 3 periods. So you can actually attach a number to each one of those durations, and we can multiply that by the probability of waiting that long before you got your job. Obviously, it's an exhaustive process. If you get a job, you're not in the pool anymore, so what's left is the unlucky ones. And it's all about luck. It's not about your skill, right? So this is a great formula to remember. Next week we may prove it, but I'm not going to do it now. I'll certainly do it in 2 weeks' time. Okay, so if Q is the finding rate for the vacancy and theta Q is the finding rate for a worker, then the duration that you can expect in a continuous time model is 1 over theta times Q, 1 over F. Okay? Similarly, the duration of a firm's posted vacancy is 1 over Q. You can show that in continuous time, you can show it in discrete time. It's a classic proof. We'll do it, like I said, in 2 weeks. Just remember that, really important. The people are all the same. So the people who have a long unemployment duration are just unlucky. In the real world, it may be because you have certain attributes that make you likely to turn down jobs or unlikely to get job offers. That's a more complicated model. But even in a model like this, if it's just luck, it's just the bathtub, you can still have long-term unemployed, but the number of people that are in that state are very low. Because you're playing this lottery. And the bathtub, if it's really a bathtub and you're hitting, you're just gonna hit the match at some point. Okay, so now it gets a little bit nasty because we have to write down this complicated model, and this is where R comes from. R is going to be endogenously determined, and I'm going to try to explain these equations very, very slowly. But it's the same logic as Pissarides. It's really the same logic. The most important thing I should alert you to right now is we're in continuous time. Okay, and I've suppressed the T subscript everywhere just to make it easier for you. Otherwise you have T's everywhere. But in any period of time, a worker that has a job has an asset value, W, big W, okay? And that asset value is now a function of your current state of productivity in the match. Okay, so you have a match, a worker and a firm, always a pair in this model. So it's not going to be just a fixed value of W. It's going to depend on the current observable known value of productivity in that instant. Now, if you own this asset and you sell it to somebody, you get W. If you take that money and put it in the bank, what do you get? In that instant, you would get R times W. That's the flow income stream that would accrue to the owner of the asset. So owning the asset means you're working, you have productivity X, and therefore W times R is the flow that you can expect, the arbitrage value of owning the asset. So that has to be equal to the actual value of owning the asset, which is the right-hand side of that first equation. I get the wage, which also depends on X. Then what happens? Then all this bad stuff can happen. It can also be good. In that little tiny instant of time dt, with lambda intensity, I can have a bad shock, which means that X, the new X, is actually below R. So the probability of getting nuked, losing the job, going into the unemployment rate, into unemployment, is this term I just showed you. Okay, so it's this one. That's like S. It's like S of the Pissarides model, except now we've got little dt. We've got little, every instant of increment of time, we have to continue to value what it's like for me. And maybe you don't get a shock. Maybe nothing happens. If nothing happens, then you've still got W. Okay, but the capital, the change, the value of losing this job would be the valuation of being unemployed again minus what I had just before I got zapped. So this is the capital loss. Associated with a value of X drawn from the hat, which is below R. F of R is the probability of getting an X that is less than R by construction. And lambda is the incidence parameter of this disaster, okay, from the worker's perspective, because the worker falls into unemployment. The worker, however, could have a good shock. So you're, like I told you, you're married, you discover some nice attribute, and now the match looks much better. Okay, so this is hard to value, but this is the probability of the shock, and the value of getting that shock, you have to think about it, all possible values of X from R to 1 could happen. And I have to weight those by the probability that each one of those happens. We use an integral to do that. And dF is the density of this shock. Okay, so think of this as just a sum of a lot of the little tiny probabilities times the capital gain that I would get. And that's what this is. This is the capital gain relative to what I had an instant ago. So this is kind of a high-powered version of Pissarides, because now things are happening, and lots of things can happen. And these are all the capital gains are all the good things that can happen, but then I can also get nuked and have a capital loss. And if nothing happens, I've still got W. Yes, Paul?
So lambda, is it a probability?
It is, strictly speaking, a Poisson intensity parameter, okay? And you can think of it as a probability, but you have to be careful, because for some value of time, it's going to exceed 1. And that doesn't work.
Yeah.
It's really for a small change in time, what is the increment, what is the probability that I associate with that increment in time?
Yeah, but then it seems to me that
It's a rate, it's a rate.
1 minus lambda, right? If we have like 2 states and then we have 1 occurring with probability lambda, and then
Yeah, but if nothing happens, then I still get W. And this is measuring the capital gain and capital loss. Otherwise, I get W. Remember, this is an arbitrage relationship. Okay, if I have the asset, I get the wage, and then something bad could happen. In the next instant, if nothing happens, I still have the asset. I haven't lost the job.
Yeah.
So in the next instant, I have W again. And these are steady state valuations. So I don't have to worry about it's harder, much harder, if you let W change. I mean, if you think about it, if you own a stock, the price of the stock can go up and down. That's hard to pick up in this model, because it would have to be the changes in all these determinants of W that could be changing in every instant. So it'd be a very, very complicated expression. This is a steady state valuation. So it's already This is, the Pissarides idea of looking at steady states carries through to the 94 paper and to the 2000 chapter 2 model. Yeah.
Does the worker here lose, like has a capital loss and capital gain with the same lambda?
Yeah.
Mm.
Yeah, because that's the beauty of it. There's an incidence parameter, and then given the incidence, what happens? Then you put your hand in and you pull out the number. So,
we're kind of
so they're
missing
separate.
in the original Pissarides model, there was like something happens plus the something doesn't happen.
That was the discrete. That's because it was a discrete time.
So we're kind of missing that here.
Yeah, but you can derive that in Pissarides. You make the period go to get really small, and you can. On the left hand side, we had W. We didn't have R times W. So you could think of the Pissarides model as having 1 plus R times W, right? Or just RW. But then you have to have the change. So they're completely. It's completely simple to go back and forth, but you have to think a little bit. So I'm going to go quickly to get finished in time, but think, if we don't, this is hard because X is always possibly different. You can always start the match this instant at a different level of firm worker productivity. That's why it's a function. So we call this a functional equation. It's an equation in a function. Unemployment's easy because we're all the same. If you're unlucky and you lose your job, you're in the pool and there's no mark on your forehead that says, I got a job, I had a job before, or I'm employable. No, we're all the same. So being unemployed in this model is fairly unpleasant. You get B. It's not based on your previous wage. It's a constant. And then there's a chance of getting something in the next instant. It's the same type of Poisson arrival, bumping into a worker. And then if you do, you get to start at the top, and you get this massive capital gain. So that's the value of the assumption of X equals 1 at the top. We don't have to worry about all the other things. You can imagine it's not so pretty. So this is pretty because U is an easy state to think about. And for the firms, it looks like a funny typo here, but it just means that PowerPoint can't handle the bracket. Very interesting. I didn't know that. Okay, so if we're a firm, our perspective, of course, is different. We want the worker to be with us. We want them to have low wages, and we want to get all the surplus for ourselves. But given that the wage has been determined somewhere else, I haven't told you how it got determined, I still need to operate with this worker. So there's this huge complementarity. If I don't have a worker, I can't produce. I can't make a profit. Okay, so the value of my asset, using the Lucas idea, is related to my current profit, and P is the price of the output. So I slip that in. Instead of being 1, it could be P. P is just the price of the output. It gives us an extra degree of freedom. So Px is the productivity of our match, and then I have to pay the worker W of X, because W is going to be a function of X. If my worker's really productive, I have to pay him more. I'm just going to tell you that, but I'll prove it in a second, maybe next week. And then all these things can happen. So again, lambda incidence intensity. If it's a bad shock, the probability is 1, is the probability of getting the new X being less than the reservation value. That would be this first probability. So you can see this is a capital loss, because having a vacancy is going to be less attractive than having a worker in hand. And then things can get better, so the marriage could improve. And we get more productivity. And it can range all these different values of X going from R to the top. Okay, probability of getting the top again has 0 measure, but I could get really close depending on the assumptions that I make. And again, the vacancy, the same thing as before, the analogy should be clear to you. I've bought a bunch of simplicity. I don't have this optimality of turning down an offer. I'm always going to accept an offer because it's always better. But after that, things can deteriorate. And as before, the firms take the next instant as given. So the firm cannot affect the future valuations of the match. That's, again, the key. It's going to help us do the Nash bargain very quickly, okay? Okay, so, this is a simplification, basically. Taking this and simplifying it, I can simplify it to that because I know some of the attributes of the problem, and then I can go to town. I can actually solve the Nash bargain. And the firm and the worker are still bargaining over one number, but now they know the productivity, and it can be different from the constant productivity of Pissarides. So the optimal wage or the wage in a Nash bargain will depend on X. So that's where the sharing happens, right? So a good shock means the worker gets a piece of the action, and the firm gets a piece of the action. The first order condition looks like before. And if we impose the steady state and a zero vacancy condition as before, I get this beautiful wage equation. Actually, this is without even imposing the zero vacancy. This is even before. Okay, this just means basically I think I did impose it. Yep, it doesn't matter. The wage is similarly a mixture of two things. One is the productivity as it stands today, now, and the fallback is the asset value I would have in flow terms if I were unemployed. That's not going to be equal to B. It's going to be B plus something. Because if I'm unemployed, I can always get a job, right? I'm not out of the job market forever. So we'll solve for you in a second. So I know this is probably very difficult, but think about it. This is very similar to Pissarides, the basic Pissarides model, except now we have the wage is kind of a markup. It's like a markup on the fallback position of the worker, and the markup will depend on what there is to share. The worker can't extract more surplus than there is. But obviously, if beta gets really close to 1, then the worker can get lots of surplus. It can get all the surplus almost. If it gets all the surplus, then maybe there won't be any posted vacancies and the whole model collapses. But for ranges in the open interval between 0 and 1, we can get lots of interesting outcomes. Okay, so I'll give you a preview of what we'll do next time, or maybe Thomas will do it in the section. We can impose the vacancy condition, and we can equate J like before. It's a beautiful parallel, and then you can solve for this what we're going to call the JC curve. It's not the VS curve; it's the job creation curve. So it's basically it's going to describe the behavior of firms imposing the zero vacancy condition and sort of describe under what conditions these vacancies will be created. Job creation, JC. That's just one. There's the other question is that jobs are being destroyed with a Poisson arrival probability measure of lambda times the probability of getting a lousy match, and we haven't derived R yet. We need to derive R, and it turns out that R is endogenous, but R will be basically the cutoff point when the firm says, okay, we call it quits, or the worker says we call it quits, and you can go at this either way. I'll do this in detail next week. Maybe Thomas will go into it a little bit in detail, but we'll take something like this knowledge and combine it with the job destruction condition, and we get this sort of mutually agreed level of R. If you look at it, you can see that it's another equation in R and in theta, when you plug in for U. We already have one equation between R and in R and theta, so we have two equations in R and theta. This one would be the destruction condition, which says basically under what conditions do the worker and the firm mutually agree that we should separate. Okay, so I'll just show you. We'll talk about this next week, but here's what the equilibrium looks like. We don't have U and V now on the axes. We have R. And then we have labor market tightness, theta, which is the ratio of V to U. Okay, so the JD curve will be upward sloping, and the JC curve is downward sloping. So we can do the same kind of comparative statics exercises with various dials or different exogenous changes to see how the market works. And I claim that you can use this to think about the German Hartz reforms. The Hartz reforms in Germany were very controversial. Okay, they cut the benefit in Germany. This is the effect of raising the benefit in the Mortensen Pissarides model. Labor market tightness goes down, and the cutoff level goes up. Okay, we'll go into the logic of that next time. So if you cut the benefit, you increase the posting of vacancies, you increase the labor market tightness outcome, and you reduce the cutoff value. And that's exactly what we observe in Germany over the past 10 or 15 years. Jobs are much more stable, so the cutoff has probably gone down. People are much less reluctant. Wages have stagnated, and the number of vacancies relative to unemployed has skyrocketed. Okay? Hartz reforms also can be thought of as a way of weakening worker bargaining power. This is what happens if you increase worker bargaining power. Okay? And of course, the Hartz III reforms increase the efficiency of matching. So that's like shifting out the curve. We'll go into detail on why that's the case next time. But if you look at Germany, you can see this is exactly what happened, and it started around 2005. That's when the Hartz reforms were. So this is controversial. People say, oh, there's so many other things going on, but I think most people agree, even if you don't like the reforms, and you can see this is why Friedrich Merz is trying to undercut the Bürgergeld reform by saying, well, why don't we just raise the Hartz reform, raise the Hartz unemployment benefit, because there's less sanction in turning down a job, or easier to separate. And I think there's clear difference of interest between the employer and the employee in this case. So you can understand that thinking about it from this perspective. So I'll stop here, and next time we'll pick up the MP model and make it even more easy to understand. Okay, good. See you next week.